Hey guys, in this video we're going to talk about Hess's law, enthalpy, and state functions. To begin with, enthalpy is that symbol delta H that you've seen before. Roughly speaking, this is the heat released or absorbed by a chemical reaction. A state function is any function where the final result is independent of the path or steps taken to get there. All right, let's give an example of a state function. Let's suppose that you are trying to drive from one place to another. The two places might be, I don't know, a house and, well, I don't know, another house. Yay, two houses. Very simple. All right, and there are two ways to get there. You could go down this street and then up this street, and then you arrive at the house. Or you could go on this street and this street, and then you arrive at the house. Literally didn't matter which path you took to get there. Either way, you'd arrive at the exact same location. This would even be true if you took some other more circuitous route, right? You could go, oh, there's a street there. You take this one, and you go around, and then you go around. There's a lot of different streets. There's a lot of different ways that you could get from this house to this house. But no matter what path you take, you are going to end up at the exact same location. Another example might be, I don't know, the money in your wallet. Let's suppose that you have $40 in your wallet, and they're both in 20s. And then you go to pay for something that costs $10. Well, all right, there's two possible ways that this reimbursement and disbursement of funds could work. Step one, you hand the guy a $20 bill. Briefly, the money in your wallet is $20. But then you are reimbursed, given your change, and now you have $30 remaining in your wallet. Okay, it's a less likely scenario here, but suppose that you said, hey man, I've only got a 20. And he says, cool, here's your change. I don't know why I'd give you your change first, but this guy did. All right, you have $50, again, briefly in your wallet. Then you pay him with a 20. Okay. Regardless of whether you first lose 20 and then gain 10, or gain 10 and then lose 20, you end up with $30. In all of these cases, these are state functions because the final result is independent of the path or steps taken to get there. Enthalpy is also a state function, which can be observed if you're looking at something called a reaction coordinate diagram. Basically, a reaction coordinate diagram shows you energy with respect to reactants versus products. So typically we will draw the reactants on the left, the products on the right, and then the idea is that in going from the reactants to products, regardless of what intermediate steps might be taken, there is the exact same change in enthalpy. Now, importantly, Hess's law is usually, in fact, used for calculating the change in enthalpy for reactions which might be difficult to directly measure for whatever reason. It's challenging to measure it, but you know the enthalpies for related reactions. And so if you can figure out the energy that it took to get from here to, say, up there, and then the energy to get to some other position down here, and then from that you can figure, and you know the energy to get from there to there, well, guess what? You have figured out, in fact, the enthalpy to go from the reactants where you started to the products where you wished to end up. Let's look at a couple of examples of this. In your notes packet, this is example 1, and it's got a simple proposition for us. We're supposed to find the enthalpy for the reaction A plus B yields D. Okay, I don't know what A, B, and D are. It also really doesn't matter. That's not the point. The point is that what you've been given is a puzzle where if you put the pieces together in the right way, you're going to be able to get the result you want or the information you want, which is exactly what is the enthalpy for A plus B yields D. All right, couple of rules here. Rule number 1. You can reverse a reaction. If you do, the sign of delta H switches. Second rule, you can multiply or divide the equation by some number. And if you do, the enthalpy changes by that exact same factor. And actually, third rule, you can add equations together. If you do, the enthalpies also add. So the entire goal is to use those three rules and the given equations to manipulate stuff to give me the result that I'm being asked to find. All right, now, how in the world am I supposed to do this? Well, first thing that jumps out at me here is that I'm supposed to have D on the right side of the equation, right? Here's D, it's on the right side of the equation, and the only equation I have that contains D is this one right here. D is on the left side. Okay, well that's no good. Why don't we begin by getting D on the side that I need it to be on? All right, need a little space here. Let's see. So that means I'm going to use rule number 1 here. You can reverse a reaction. If you do, delta H switches. So I'm going to write 2C plus B yields 2D. And the enthalpy for this process is now positive 55. All right, now let's just rewrite the first equation I was given directly above it. And what I will now do is add the two equations together. Mr. Errico, why are we doing this? What is the good of that? Well, here's the good of it. You should notice, or you might have noticed, or well, you will notice, that there's 2C on each side of the equation. And just like how in math class, if you had something like 2x plus y equals 2x, I don't know, minus 5 or something. If you subtracted 2x from both sides, well, the result would be that x would disappear entirely because you've got the same amount of x's on each side of the equation. So if I take those two equations and I add them together, the result is going to be that the c's will eliminate because I have the exact same number of c's on each side of the equation. So gone. Now I have 2a plus 2b, because b plus b is, of course, 2b, yields 2d. And the enthalpy for this reaction would be whatever 120, or whatever negative 125 plus 55 is, which darn well better be negative 70, otherwise this will be embarrassing. Okay, next though, I didn't want to know what 2a plus 2b yields. I wanted to know A plus B yields D. Like, what's the enthalpy for that reaction? Okay, well, that's where we end up with our use of rule number 2, which is you can multiply or divide by a number. Conveniently, in this case, we've got a factor of 2 present everywhere. And so what I can do is I can divide both sides of the equation by 2. The result then is going to be, if I divide everything by 2, I now get A plus B yields D. Again, what I did there was I divided by 2 on both sides. All right, this also divides the enthalpy by 2, so it looks like the enthalpy for this process is going to be negative 35 kilojoules. Lovely. Let's put a box around it. Great. Now, why don't you try example 2? Pause the video, resume once you think you've got it, and check out my work and see if you get the same answer as me. If you don't get the same answer, try and figure out where you went wrong. So pause the video, I'll work it out. And there we have it. Really, this one had almost the exact same steps as the previous one, so wasn't that different. But go ahead and try out example 3 next. Example 3 is going to involve some different steps. Pause the video, please. Try it out on your own now that you understand the basic idea of what to do, and then resume once you think you've got it or if you get stuck. In this case, when you get to the step where you add the equations together, the sulfurs will entirely eliminate. But you can see that there are 2 oxygens on the right side of this equation and 3 on the right side of, or left side of the other one. The result is going to be that the oxygen is not entirely eliminated. Rather, you will have 1 O2 molecule remaining on the left, because 3 minus 2 is, of course, 1. And this indeed yields the result that we wanted, right? That's the equation I wanted. All right, so now we just add the enthalpies together. And we appear to have negative 198.2 kilojoules. It's pretty much always going to be kilojoules. All right, when you see example 4, you'll notice this one is a bit more complicated. There's 3 equations that we somehow have to fit together. Try it on your own first and then resume the video if you're stuck or you just want to see if you got the right answer. And there we have it. All right, the last one is important to look at because this one involves a fractional coefficient, which you have never seen before. So yes, I am skipping over example 5. You can figure that one out as similar to example 4. But example 6 definitely needs to be looked at because of, whoa, what is going on right here with this 1/2? Well, all right. I agree that there isn't such a thing as half of an O2 molecule, at least not exactly. But that doesn't stop chemists from being able to write equations like this. So the utility of it is sometimes it's more convenient to have, a coefficient of 1 because there's much less math involved. All right, fine. Whatever it may be, it is legal under certain circumstances to write equations like this, and so we do. All right, I wanted you to see this one because it's possible that in the homework you will see some where fractional coefficients do come up. The math here works exactly the same as anything else, right? If I took that equation and I multiplied by 2, I'd multiply all the coefficients by 2, and also the enthalpy by 2. All right, so nothing untoward or weird there, right? We'd just get 2H2 plus O2 yields 2H2O, and the enthalpy for it would be precisely 2 times this one up here. Gosh, I hope that works out correctly. All right, now back to the real question here. How do I get this equation that they are asking us to find? Boy. Turns out you can't because there's in fact a typo. The equation that you were given up here is unbalanced. It should say 2. Well, let's fix that. Anyway, so there's supposed to be a 2 there. And now it's actually possible to get the indicated equation. Okay, so first thing that jumps out at me is the aluminums are off. So let's try doubling that first equation. Next, the equation I want doesn't have any water in it and doesn't have any hydrogen in it. So let's take my equation in red, and we're going to multiply that by 3. I picked 3 because that's the factor by which 2 and 6 differ. So if I triple that equation, that will give me 6 hydrogens on the left to cancel out the 6 hydrogens on the right. Oh, and look at that beautifully. It also works out that the 6 waters will eliminate. Okay, and yes, that will indeed eliminate some of those undesirable components. No more hydrogen, no more water, and the final result is the equation that I was looking for. Oop, that, wow. 2Al2O3 with an enthalpy of, okay, negative 3,339.8 it is. Ah, but wait, because of sig figs, there's one final thing to do. Our answer has to be rounded to the ones place. And there it is. Don't forget the decimal point. Okay, I hope that helps, and I will see you in class.